Hi everyone, I am Rosa Mikalo, BSE Science 3 student, and this is Regional Wind Pattern. The learning objectives are: understand the concept of regional wind patterns, identify the driving forces of the regional wind patterns, and explain how these forces influence the wind direction. The forces governing the wind patterns are pressure gradient force, Coriolis force, and frictional force. Pressure gradient simply differences in pressure over a distance, and it is this differences in pressure that leads to pressure gradient force, which is one of the fundamental driving forces of wind. To really understand how the pressure gradient force works, what you must know is this: air naturally flows from areas of higher pressure to areas of lower pressure. To illustrate this, let us suppose that the point A has a pressure of 1013 millibars and point B has a pressure of 997 millibars. Well, because of the pressure difference, air will naturally flow from point A, area of higher pressure, to point B, the area of lower pressure. Now, the greater the difference in the pressure, the faster the flow of the air will be. In other words, the wind will be higher. In weather maps, we can see the pressure gradient by means of isobars, which are the lines of same pressure. The closer the isobars are to each other, the faster the wind is in the particular area. To show wind speeds, the pressure gradient is plotted into weather maps using isobars mapped between areas of high and low pressure. Bars spaced far apart represents a gradual pressure gradient and light winds. Those closer together show a steep pressure gradient and strong winds. Winds can also occur in large regional scale. One example of this type is the wind would be katabatic winds. These are winds caused by gravity and are sometimes called drainage winds because they drain down the valley or slope when dense, cold air at high elevation flows downhill by gravity. The seasonal shifting monsoonal winds found in Southeast Asia, Indonesia, India, Northern Australia, and Equatorial Africa are another example of regional winds because they are confined to the larger region and tropics as opposed to just India, for example. Coriolis force. This is caused by the rotation of the Earth. The Earth rotates faster around its equator than it does in its pole. This is because points near the equator of the Earth have farther to travel in a day or in a 24-hour period than points closer to the poles. This explains the differences in the rotational speed of the Earth on its equator compared to the poles, and this has an impact on the direction of the wind in the North and South Hemisphere. The development of weather patterns such as cyclones and trade winds are examples of the impact of the Coriolis effect. Cyclones are low-pressure systems that suck air into their center or the eye. In Northern Hemisphere, fluids from high-pressure system pass low-pressure system to the right. As air masses are pulled into cyclones from all directions, they are deflected, and the storm system or a hurricane seems to rotate counterclockwise. In Southern Hemisphere, currents are deflected to the left. As a result, storm system seems to rotate clockwise. Outside storm systems, the impact of Coriolis effect helped define regular wind patterns around the globe. The weather impacting fast-moving objects such as airplanes and rockets is influenced by the Coriolis effect. The direction of prevailing winds are largely determined by the Coriolis effect, and pilots must take that into account when charting flight paths over long distances. Military snipers sometimes have to consider the Coriolis effect. Although the trajectory of bullets is too short to be greatly impacted by the Earth's rotation, the sniper targeting is so precise that a deflection of several centimeters could injure innocent people or damage civilian infrastructure. Polar power. The Coriolis force is strongest near the poles and absent at the equator. Cyclones need the Coriolis force in order to circulate. For this reason, Hurricanes almost never occur in equatorial regions and never cross the equator itself. The last driving force is friction. Friction only influences the direction of wind when it is close to the Earth's surface, and that is typically defined as less than 700 feet above the surface of the Earth. When wind is close to the ground, it is affected by friction of objects and topography of the surface. But once we get over 700 feet above the surface of the Earth, friction will no longer have a measurable impact on the direction of the wind. In meteorology, friction is important because it causes the wind speeds at the surface to be less and more turbulent than they otherwise would be. Rough terrain is more effective in decreasing the wind speed and water surface. Friction processes can help promote surface convergence and uplift. In summary, the wind is controlled by the pressure gradient force, the Coriolis force, and friction. Wind speed is primarily dictated by the pressure gradient force, while all three controllers combine to guide the wind direction.